Look at some examples. The expected amount of product, is called either the predicted or theoretical yield. So it's when we did those labs, it was your prediction. So in theory, it's what we should get. That's why it's either predicted or theoretical. The quantity of the product actually obtained, so like if you did an experiment, what you actually measured out is called the experimental or actual yield. Which makes sense because it's what you get if you did an experiment. And it's like the actual value when you put it on the weigh scale, that's the number you got. Okay. It is extremely rare for the predicted and the experimental to be the same. So there could be sources of error. Okay? So factors affecting the experimental yield will include these things, and we could say that these are things that are sources of error. So make a note to yourself that these factors we could say are also called sources of error. So when you're asked that on the lab, sources of error. So in science, when you're giving sources of error, it can't be things that are like, I did my calculations wrong. It can't be like something that you like if you actually did something wrong in the experiment, that's not a source of error. You just did the whole experiment wrong. Like you wouldn't, so then your results wouldn't be valid. Okay? Having more precise methods is one thing, but if it's like says, okay, this is how I did it, and I followed it exactly, then it's not a source of error. You know what I mean? But you could still be more precise. But if you're like, yeah, I didn't do what the lab said, that's why I got like 95% error. Well, that's not really a valid source of error. It's just you did it wrong. Okay? So doing it wrong is different than being able to be more precise. Okay? So number one, two chemicals can react to give different products. So your reactants might not make the products that you would want them to. They can make different things. So called competing reactions. So you might set things up to happen a certain way, but it might not obey that exact one chemical equation that you would hope for. Another thing, so that's like example, carbon and oxygen can react to either form carbon dioxide or carbon monoxide, okay? And so those are competing reactions. Another thing is that the reaction could be, sorry, are you guys writing down the example? You didn't have that down. Okay, I'll give you a second. So carbon and oxygen can react to form carbon dioxide or carbon monoxide. Also, a reaction could be very slow. So if a reaction, like say you write out your chemical equation, well, in order for that to happen, say it would have to take 10 years. Well, you can't just like, you know, so say you want to take iron and you want to measure iron oxide after it's been rusted, okay? well, you're gonna have to sit there with your iron for a long time. It will rust, but it, takes a little while, right? So you can't measure like iron oxide in 2 minutes. Like that's not really going to tell you much about about its rust. Okay, so if reactions are very slow, either you need to speed them up with something called a catalyst, or you have to measure it over a really long time. Other things like collection and transfer methods. So these are things that would increase your precision. It's not saying like, oh, I didn't use a pipette, I just used a graduated cylinder. Okay, well, did you have a pipette? Yes. Did you use it? No. Okay, well, that's just being wrong then. Okay? But it's like, okay, more like with the stir stick, when we were doing our precipitate lab, if you didn't wash off the stir stick every time, that's like a precision thing in the collection, right? Like that could kind of throw it off. The reactant or product purity. So if it's all of what it says it should be, or if there's some other impurities in there. Or the reaction doesn't go to completion. That's kind of the same as the reaction is very slow. So all of these things could kind of make our experimental results different. But actually, lately, you guys have been getting extremely good results. Minus that one where some of you got like 67% error, but it's okay. Okay, oops. All right. Ideally, percent yield should be as close to 100% as possible, the percent yield, okay? Very important. Percent yield is this formula. Percent yield is equal to actual divided by predicted times by 100. So think about yield, think about like a yield of a crop, right? It's like a measure of how much you made versus how much you planted. Okay? You're familiar with that type of lingo, so use that to help remember. So we can also calculate our percent error. So this is something different. Percent error is something different for the experiment, which tells us how far we are from the theoretical yield. The closer to 0% error is, the better the experiment.